Hi there, welcome back. So we continue our discussion about the current meter, and this time we are going to discuss a special type of current meter with little modification to the basic current meter. And this name of this new circuit is called as Buford Feedback Current Mirror. So as you can see on your screen to the left of mine, I have this current meter with the transistor Q1 and Q2, and we have seen the basic of this circuit, how it operates. I will use the resistor R to set the I reference current from the available voltage supply V plus, and the transistor pins, collector, base, and the emitters are arranged in this fashion so that I have biased collector and the base pins together, and that makes the transistor Q1 as a to operate as a simple PN junction diode with these IV characteristics of a diode. And we make sure that with such arrangement, this transistor operates in the linear region of operation. And then I said that if Q1 and Q2 are exactly same with their part numbers from the manufacturer, their beta values, which are the current gain, DC current gain, are same, and their other properties are also same, such as their IC max and VCO open circuits. So if Q1 and Q2 are same, I said I out will be exactly or approximately equal to the input current I reference, right? But in practically, since there is two currents, that is the base currents of the transistor Q1 and Q2, IB1 and IB2, they have some finite values. So in the final expression, I out would not be exactly equal to I reference, rather it would be I reference minus 2 times IB, where this 2 times IB comes from the finite values of the base currents. So this circuit still works considerably well, provided we just fulfill the condition of matching the two transistors exactly, and then maintaining the minimum output voltage across the transistor Q2 so that it operates or remains in the linear region of operation. Linear region of operation indicates it will have the constant current across the minimum voltage, that is V out min, would be here, and above that, for any value of V out above this V out minimum, this will stay in the linear region of operation, uh, eventually satisfying the condition that the voltage at the collector of the transistor, which is V out, would match the voltage right here. Okay, and we also said that this VBE, which is generated due to applied I reference, acts as an input to this transistor Q2. But now the problem is to how to remove this error, gain error, caused by the finite base current of transistor Q1 and Q2. So to circumvent this problem, we have such arrangement about, as you can see on the screen into my right, I have used exactly Q1 and Q2 in the same way, but instead of connecting its pin collector and base together, I make sure that I don't connect a Q1 in a diode connected fashion. Rather, I use the transistor Q3 as a common emitter configuration, which acts as an emitter follower. It is a voltage buffer, and it is a good current amplifier. So what I'm doing here, the voltage at the collector right here is one junction drop, base emitter junction drop of the transistor Q3 above the emitter voltage of the Q3, which is the base voltage of Q1 and Q2. Okay, I repeat, the voltage at this point, that is at the base of Q3 or at the collector of Q1, is VBE plus VE, okay, or VE which is the voltage here at the emitter of Q3, will be VC minus VB. So that's how the emitter follower works. So because of that, since the beta of the Q3 is large, is very, very greater than 1, we have an action of negative feedback to reduce the gain of this finite error gain caused by the transistor Q1 and Q2. So let us analyze this circuit little bit about how this circuit is going to work. So you have this voltage source from which I am using the resistor R to draw the current I reference. Then this current is splitted into two parts, which is IB3, and then here I have IC3, and then I see here I have this junction voltage, as I said before, that is VBE3. Here I have the voltage VE, which is also equal to VB1 equal to VB2, which is VB1 is equal to VB2 equal to VB. So that's how I have this voltage. And then I have this voltages VBE1 is equal to VBE2. So that's exactly what I want. And Q1 and Q2 are identical. And here is output current that will more closely matching the input reference, removing the finite base current. So the current IB1 here, and this current is IB2. I will write here IB2. Okay, so now the voltage at the collector, as I said, will come here as an emitter follower, and that voltage will regulate due to in this loop, the output current will be matched to the reference current. In a moment, we see that. But before that, let me write the expression about how the what would be the value of I reference here. The I reference is simply I reference is equal to V plus minus VBE divided by R, VB1 or VB2, because you see the collector and the base are shorted. So your VCE is equal to VBE here. But in this case, for this circuit, I would say I reference would be, let's say, V plus minus minus this drop VB3 plus the drop VB1 or VB2. So I would say VBE3 minus VBE1 or 2 divided by resistor R. Assuming I have the VB of all transistors same, 0.7 if they are silicon transistor, I would say I reference is equal to V plus minus twice VBE divided by R. So that's how I have. So again, R will change, then the input current will change. So it is just for the demonstration I'm using R. Rather, I would need a dedicated circuitry to generate the input reference current. Okay, now I have to make sure that the V out minimum voltage across the output transistor should be at the same potential, the voltage at of the transistor Q1, collector voltage of transistor Q1. Then only I out will be exactly equal to I reference. Okay, so now exercise for you. In one of our previous video, I have explained to you how the negative feedback work. Exercise for you would be to write in the comment box if there is a change in the I out, you have to tell me how the output current matches the mirrors the reference current. Okay, or in other simple words, tell me how the negative feedback will work so that output current will be equal to reference current.